also starting the whiteboard. Okay. Yeah. So please, you can go ahead and ask any queries, doubts from those two lectures. One more chance. Any questions, any queries?
So can you tell that Maxwell square, how to use that to remember?
How to use that? Okay. So that was just a way of remembering Maxwell relationships. So that's really the only use of that Maxwell square. Can you tell me which page introduce that on? Yeah, you can see that. So you can see the whiteboard, all of you.
Yes, sir, the whiteboard only.
This is how we made it. There were four Maxwell relationships, and really the main thing of this was if you want to memorize. Okay, and oh wow, if it's resetting or it just got deleted everything. Okay, anyways, it seems it's got deleted. So I assume you can see the Maxwell square. So the way you can use it is, for example, you go to the corners. Okay. So one of the relationships there was the partial derivative of temperature with respect to volume. So those are two, let's say the right corners of the square. And then the opposite side, somehow it is just acting. On the opposite side, not used this before, and somehow today my OneNote is not working well.
I guess you need to.
Just
It's there. Just it's zoomed out.
say do what?
You need to zoom out. The screen is just moving.
Okay, you are right. Okay, so then I can populate this. So you had minus p and t, right? So I want the partial derivative of t with respect to v. And then to keep the variable constant, which to know, kind of remember which variable to keep constant, I go to the opposite side and I see s there. Okay, holding s and holding minus s constant is the same thing. Okay, so even though on the opposite edge I have minus s, but holding minus s constant is same as saying holding s constant. So I'm just writing s. Okay, and on the other sides now the corresponding derivative on the right hand side would be you take these two. Okay, so some of these minus signs you will need to still remember, because even though I am having minus and minus p both, but still I have a minus sign here, and the variable to hold constant would be on the opposite end, which is v. Okay, so that is how you can use the Maxwell square. So actually, if you want, you can remove u here. I'm not using u in this case. So I've just used the four corners. That is how you can build other relationships also. And main thing which it tells you, that means the output of the square, or let's say the utility of Maxwell relationships, is that it allows you to convert from one partial derivative to another. And on the immediate next page, that means page 7 in the lecture, I've shown one application of this. Okay, some of these partial derivatives might be available to me from experiments from equation of state. Others might not be available directly. So by using these conversions, I can go from the unknown partial derivative to a known partial derivative. Okay, and example of that is on page 7. So immediately after the Maxwell square page, on page 7, I'm showing you how these relationships can be useful. Okay, but this is specifically how you can use the Maxwell square.
Okay, yes. Just the sign needs to be taken care of manually. Rest is
Yes, sign is something, but yeah, the four or whatever the thermodynamic properties, the state variables which you need to use, you can see from this Maxwell square. Okay, so I'm getting T and V on one side. I'm holding S constant, which is opposite to V on the same end. And then on the other side, I have P and S. And then opposite to S, I have V. So I'm holding V constant. So that is how I can remember from the square this relationship. And anyways, you have the textbook, so and the lecture notes. So per se, it's not very important that you really memorize these relationships. Just know how to use them. Okay. Any other questions, queries?
so you discussed about that case where the gas just got expanded. Uh, there was a partition and we removed the partition. That question.
That one of them was in problem in chapter 2.
Huh.
Can you tell me?
Nahin,
Okay, tell me what about.
legendary as well. In legendary transform topic, you discussed it, and you just said that the gas and vacuum, that partition when it was there, that state was non-equilibrium. So how is that non-equilibrium with respect to, I mean, just the gas system? It's equilibrium, right?
No, no. Okay, so the example. So when the partition is present, this was an equilibrium state. Okay. However, what I was referring to was the moment when this partition is ruptured, but the full redistribution of gas has not happened. Okay. So the instant which we are looking at is this red one. At the instant when rupture occurs, this red color is not, it is showing something else. So let's just remove. So the instant when the rupture has happened, but no redistribution of gas has yet happened, that is clearly a non-equilibrium state. Because I know at equilibrium, this gas will now occupy the entire volume. Okay, so I'm specifically referring to this instant when rupture has happened. Okay, that is a non-equilibrium state. Is it clear now?
Yes, sir.
Okay, and this will evolve to a new equilibrium state. And we already know from chapter 2 that new equilibrium state is a state at the same temperature actually. We did the calculation. And with the gas, same mass of gas occupying the entire volume. Any other query, questions? So let me discuss one problem. We might discuss more also. A minor exam I will discuss next week because this Thursday I will not be able to take the class. So I want to cover some problem solving aspects so that you can actually practice because as far as the pure species are concerned, this is the most important chapter in terms of problem solving because it is combining several concepts and therefore you can see this problem sheet is quite lengthy compared to other chapters. The reason is it's number one, allowing us to do calculations for more realistic scenarios. Number two, because we are doing calculations for real species, the variety is huge. Okay, so we need to address at least some of that variety. Therefore, those are two prime reasons why this problem sheet is much bigger. Okay. And you will see throughout the problem sheet several practical examples coming up. All right. So this is one question which was briefly discussed in the lecture class. Sorry that this is just all over the place. Has anyone else used this whiteboard before? Anyway, it's just for today. All right. So, any help with how to stop this automatic zoom would be appreciated if anyone knows. Okay. So there's a throttle process from state 1 to state 2. So up to this point, you would say we have solved this kind of problem. Okay, in chapter 2, maybe again in chapter 3, it came up. Okay, so we have in some sense solved this problem. However, the main change was we are no longer restricted to ideal gases. Okay, and that is the theme throughout this chapter. I think most of the problems, if not all, you are dealing with real state, not restricting your calculation to the ideal gas phase. Okay, so now for state 1, two possible cases were given. Either I have a superheated vapor state as the inlet for state 1, or I have a subcooled liquid state. Okay, so these were the two scenarios given. Now state 2, for the superheated vapor case, you can show that you will again end up in a superheated vapors, but different pressure and temperature. Okay, so state point will change, but the phase doesn't change. And in case 2, various possibilities exist theoretically. Okay, of course, there'll be one specific answer you will get, but depending on the inlet pressure temperature, you might get many different answers. Okay, so this is kind of what was already covered in the lecture class, these possibilities. And I also showed the end calculations. That means the end numbers. So now I'm going to discuss how to do those calculations, how to calculate those enthalpy changes in the process. Okay. So I will start with case 1, the easier one, where I have a superheated vapor. I don't know what pressure and temperature I had mentioned there. So pressure was what? 15? Yeah, I think. Yeah, 115 atmosphere. And temperature
447.
again. What's the value?
447 kelvins.
447 Kelvin. Thank you. So this is the inlet, okay, superheated vapor state, and outlet
1 atmosphere.
1 atmosphere is given, and T is the unknown. So this is what has happened here. So now, if I say without proof, because I'm going to show you the alternate calculation anyways, assume ideal gas at inlet and outlet. Then can you tell me what is the temperature at the outlet? If I'm asking you, then maybe the answer is very simple. Throttle delta H is 0. And if you are modeling it as an ideal gas, so if ideal gas enthalpy change is 0, temperature change would be 0. Temperature at the outlet is 447 Kelvin. Okay. But then someone says that no, especially at state 1, pressure is high. So ideal gas assumption would be wrong. Okay. So we trust the person and say that, okay, let's do an alternate calculation. Okay. So now what is that alternate calculation? What is the possibility? I can model, that means I need to model the states as real gas. Okay. So I will do the simple within this still one simplification. So I will say real gas at state 1 but I'm not letting go of ideal gas assumption entirely. So I'm saying that, okay, no, still I'm going to take ideal gas at state 2. Okay, and this is just for illustrative purposes. And actually, if you do the calculation, you would see that ideal gas at state 2 is actually a very reasonable approximation. So I'm not doing anything out of ordinary. Okay, so making this ideal gas assumption at state 2 is still perfectly all right. Okay, however, at state 1, clearly the pressure is high and you need to relax that. Okay? So now the enthalpy change in going from state 1 to state 2, H2 minus H1. Enthalpy of state 2, we are saying we can still write it as ideal gas. So H2 I replace by H2 Ig. However, enthalpy of state 1, because we are considering this as a real gas, so I have to add the residual. Okay, so this concept of residuals is discussed in the lecture class and it is a very, very important concept because it allows you to do calculations for real gases. And all of this calculation will happen at P1 T1. Calculation of H2 under the ideal gas approximation will happen at P2 T2. If I further say even at state 2, you have to model it as a real gas, you can still do the calculation, but you will need to do it in an iterative fashion. The reason being, temperature at state 2 is not known. To calculate the residuals, you need temperature, and the temperature will come after the residuals. Is it clear? H2, if I model as a real gas, then I need to know the residual at state 2. The residual at state 2 will depend on temperature of state 2, and temperature of state 2 is the unknown here. Okay, so there will be some coupling involved. So it's not that you cannot solve it, but you will need to follow an iterative process. So from here, what I get is delta H for the ideal gas in going from state 1 to state 2, where state 1 is P1 T1, state 2 is P2 T2, and you also have to calculate the residual at P1 T1. Okay, and here you calculate the PR/TR in state 1. And what you will see once you calculate the PR/TR in state 1, you can go to your chapter 3, look at the applicability of Pitzer second virial correlations. You would see here that Pitzer second virial correlations are valid. So either you can use Pitzer second virial correlations or you can use the Less-Kessler correlations. The tables for Less-Kessler are available in the book. The equations for Pitzer second virial correlations are also available in the book. So either way, you can calculate H1R. Okay. And this delta Hij will not depend on pressure change. So for an ideal gas, it will be simply an integral of CPdt from T1 to T2. And H1R also you have calculated. This needs to be equal to 0 because the throttle process delta H needs to be 0. So the only unknown is T2. If you do this calculation, I'm leaving the last part to you. The temperature comes out, sorry. temperature comes out to be 436 Kelvin. So instead of 447 Kelvin, under the ideal gas approximation, if you model state 1 as real gas, temperature comes out to be 436 Kelvin. That means you will get some cooling on throttling, but not a whole lot. Okay. Any questions, any queries on this part? All right. Now let's go to the second scenario, which requires more calculations, which requires more data. So for that, I will first show the process on the PV diagram. This has been done in the lecture class also. So your case 1 or scenario 1 corresponded to starting in superheated vapor and ending in a superheated vapor. So you went from 1 to 2 during your throttle. Okay, and you can see from this diagram also, for 2 prime ideal gas might be valid, whereas for 1 prime it might not be valid. That can happen because 2 prime is moving towards the region where ideal gas approximation is more accurate. Okay, low pressure. So even though there is a small decrease in temperature from 447 Kelvin, you have gone to 436 Kelvin. So if I only look at temperature, I would say why ideal gas is valid. However, the main change which has happened in going from 1 prime to 2 prime is a large decrease in pressure, which made the applicability of ideal gas approximation at state 2 prime more accurate. Okay. Can someone tell if at state point 2 also you want to relax the assumption and you want to model this as a real gas at 2 prime also? What will be the procedure? How will you go about it?
So by introducing the reduced variable, right? HR.
No, that is fine. But now, see, here the emphasis is on specifics. So tell exactly what steps you will do to complete the calculation. Chapter 6, it will look very easy if you try to do it in mind. But if you actually go about solving these problems, they won't be that easy. They will require some practice. So what is the protocol? What is the suggested protocol in completing this calculation if state 2 is also going to be modeled as a real gas? Option 1, use Pitzer second virial correlations. At state 2 also, you would be obtaining H2R as an analytical function of temperature, or TR. Okay, TR or T is same. Okay, so the only difference would be right now I obtained a linear or maybe a quadratic, because in this case the CP was taken to be a linear function of temperature for simplicity. So I obtained a quadratic in temperature, which I was able to solve using the roots of quadratic. Okay, however, if you now further add the details from Pitzer second virial correlations, then so this option 1 says use Pitzer second virial correlations at state 2 also. You will obtain an implicit equation in temperature in the unknown, which you can solve by numerical schemes. Okay. Option 2, if I say that no, the conditions are such that Pitzer second virial correlations are not valid, rather you need to use less Kessler. So now because less Kessler are in form of a table, I will not get any kind of equation. Even an implicit equation in temperature will not be available. So then what I will do is, the procedure would be First, I will assume ideal gas at state 2 and then calculate temperature. I've already seen that example. I will get 436 Kelvin. Okay, now calculate the residual at the temperature from the previous iteration and calculate the new estimate of T2, the improved estimate of T2, and then repeat. Okay, so that is your option 2. So model it as ideal gas at state 2, calculate the temperature, use that temperature to calculate the residual, use that residual to calculate the new value of temperature, and again you can do Picard mixing also. So once you have obtained two estimates for temperature, you can mix the old and the new solutions. So that is a Picard mixing procedure if convergence is an issue. All right. So that is on the left hand side. And even though I'm discussing it for a specific problem, the methods I'm discussing here would be valid, would be useful for a lot of problems in chapter 6. Okay. Now let us come to the other side of this, where the pressure has been, yes.
So this calculation of HR, it is the equation 6.14 now in the lecture.
I don't know equation number. Let me take a look. Equation, tell me which equation you were saying? 6.14. Which page it is?
This second last page, it was lecture 12.
Lecture 12, second last page. Okay. Yes, tell me which equation you were saying? 6.16.
6.14a.
6.14. Yes, you can use, yeah. So you can use that route also. For that, you need an equation of state. So you need an equation for Z. So these less Kessler correlations were made exactly like that. So 6.14a, 6.14b. Combine them with chapter 3, where you had expressions for Z, the compressibility factor, okay? You can combine those two to get the desired relationship. Okay, so let me show you. So
sir, is there other method as well, like apart from this, what you were talking about?
no. So it is the so let me just explain that. So we'll return to this problem. So this was an important question: how to calculate HR and SR in practice, starting at equation 6.14a and b. Okay. So this is what I want to do. Okay, I want to start at 6.14a, b, and I want to get HR and SR. Okay. So I will show you example of one case. I'm going to use a 3-parameter equation of state. And even for this 3-parameter equation of state, I have two options: less Kessler correlations and the simplified Pitzer second virial correlations. Okay. Sometimes we refer to both of them as Pitzer correlations. So this is the functional form: Z equal to Z naught, which is a function of PRTR, plus omega, which is the eccentric factor, Z1, which is again a function of PRTR. And then the only difference between less Kessler and Pitzer second virial is less Kessler provides you tables for Z0, Z1. Pitzer second virial correlations are providing you analytical forms for Z0 and Z1. Okay. So that's the main difference between the two. So since both of them are in terms of reduced variables, so I will rewrite equation 6.14 A and B. Let me show you for one. Other case you can do yourself or see from the book in terms of reduced pressure and temperature. So inside the integral, I'm using PR prime as a dummy variable because PR I'm using as the limit. Okay, so one of the limits, the upper limit is PR. So therefore, I'm using PR prime inside the integrand, in the integrand, which is a dummy variable. All right. So this is the expression I'm going to use. All right. Now I have two options for Z. So for this Z, if I'm going to use the less Kessler tables, then I will need to do numerical differentiation, numerical integration. So first I need to find out the derivative dz by dtr at a fixed PR from the tabulated data. So for that, I will do numerical differentiation. For example, let's say I use the central difference scheme. And then after calculating the derivative, I need to do integration from 0 to PR. Again, because the data is available in tabulated form, I will do numerical integration. Okay. So Les Kessler did that. And they provided you more tables. This time for HR and SR. And again, these tables have two parts. The first coefficient, which is written in term or reported in terms of HR by RTC. So this makes the coefficient dimensionless. R into temperature has units of energy enthalpy H has units of energy. Okay, so this ratio is dimensionless. Okay. So this HR by RTC 0, HR by RTC 1 is again tabulated in one of the appendices in the book. Similarly for SR. Okay, so that is one option. Option 2, if I want to use the Pitzer second variable, and actually this would be applicable for equation of state route also, because again equation of state you will have an expression for Z. So according to Pitzer second variable, this is the starting point. And then they had given us the expression for B. In terms of B0 and B1, which are functions of temperature only. So if you want to use this route, substitute the Z in terms of B in equation 6.14, and this is the simple form you will get. I'm giving you the final answer, which you will get after performing the differentiation and integration and realizing that B is a function of temperature only. Similarly for SR, so you can very easily write a code for doing these calculations. Okay, this is what you will get. And now this B expression is already available from chapter 3. So, and this of course you can generalize further. And again, in research papers, it has been generalized where instead of Pitzer second variable, you are going to use the cubic equation of state for Z. Again, the procedure will be same, maths will change. So I can use a cubic equation of state for Z, substitute in equation 6.14 and obtain expressions for reduce enthalpy, reduce entropy. All right. Any queries, any questions on this route? Okay, so now we can go back to this throttle example. So in the alternate scenario, I am starting with the subcooled liquid at same pressure as 1 prime, 15 bar, but the temperature is different. Okay, so temperature now is below Tsat. Therefore, I'm getting a subcooled liquid. And I also know in state 2, the pressure is 1 bar. So that is the only bit of information I have. And further, I know in going from state 1 to state 2, delta H is 0. Total process. Okay. However, now you can see that I have many possibilities. And out of these many possibilities, only one satisfies our requirement of delta H equal to 0. And that would be our answer. Okay, so that is how I will find the unique answer. Out of these many possible end states, end state could be a subcooled liquid, end state could be a saturated liquid with quality 0. It could be liquid vapor coexistence, it could be saturated vapor with quality 1, or it could be a superheated vapor. All of those possibilities exist, but only one of them will satisfy the requirement of delta H equal to 0, and that would be the state where you will end at. Okay, so let us see how I will do this calculation.
So they would not
Yes,
transition from for end state would be unsaturated liquid. There wouldn't be case that now.
in principle it can happen, right? Why it can't happen?
Okay, so we are just not.
Okay, it could be a subcooled liquid also. So all possibilities are there. Okay, but there is only one correct answer. So the throttle problem continued here. I'm extremely sorry for this mess a little bit. Okay, my pencil is broken, therefore I'm using some other resources. Anyways, so at state 1, now I have a liquid. The state point conditions are fully specified. 15 atmosphere, 70 degrees Celsius. So this is what has been given to me. Okay. At this state point, without any loss of generality, I say I am going to take this as my reference state. There is no assumption here. I'm just defining my reference. I am thermodynamics. I'm free to define one reference. So that one reference I'm defining is enthalpy of liquid, subcooled liquid in state 1. I'm saying is my reference point. So I'm taking that to be 0. And from here, because delta H is 0, so I conclude that enthalpy of state 2, I don't know the state of state 2. I don't know the temperature. I don't know what kind of phase is present there. But I know its enthalpy. So H2 is equal to 0. So now that means about state 2, we have 2 bits of information. Pressure in state 2 is known to me, 1 atmosphere. And enthalpy of state 2. Okay, it is not absolute enthalpy. It is enthalpy of state 2 defined with respect to our reference. Okay, so enthalpy of state 2 with respect to our reference is 0. Now let us complete the calculation. So let's say this point represents saturated liquid. So all of this, I'm just drawing a line at 1 bar. And this next point represents saturated vapor. So if I go here, I will get subcooled liquid. If I go here, I will get superheated vapor. So you can clearly see that the two important points are saturated liquid and saturated vapor. So if I can somehow calculate these two values, that means what I need is enthalpy of saturated liquid and saturated vapor at state point 2. I will be able to solve this problem. Okay. So again, I'm going to divide this in parts. So first I will give you the answers. I will give you the answers of HL set and HP set. I will later tell you how I calculated those. But to complete the calculation first, I will give you the answer. So at a pressure of 1 atmosphere, because I'm talking about a pure species, saturated states, there is only 1 degree of freedom. And that degree of freedom is the pressure. So if I know the pressure, I can calculate these two values. Again, these two values I have calculated again with respect to same reference. I cannot change my reference point while solving the problem. So once I fixed it, H1L equal to 0. For all other values of enthalpy, I'm doing my calculation with respect to that reference point, even though I'm not going to say that explicitly every time. Okay, units are joules per mole. So 10468.42 for the vapor. I got a value of 11,931.58. Okay. So these are the two values I obtained. Also, I know H2, that means the enthalpy of state 2, whatever it is, whatever phase it is in, must be equal to 0. So using this information, can you now tell me what is the phase in state 2? So rather than temperature, I'm first asking you what is the phase of state 2? With this level of participation, we will never be able to cover chapter 6 even in 5 tutorials. So again, maybe take this as a warning. Unless and until you are working on this chapter problems, you will not be able to follow in the tutorial, will not be able to solve many problems. Okay, yeah, someone was trying to say something maybe.
It will be liquid plus vapor
Why?
because H2 is 0 and it is between the negative and the positive value.
Perfect. Okay. So even though right now we don't know how to calculate HL sat and HV sat, but I can tell once I'm able to get these values, it would be in between. Okay. So we have managed at least something. So at state 2, I can say I have liquid plus vapor coexistence, and pressure is of course given to me. Pressure is 1 bar. Okay. So our knowledge about state 2 has increased. What is the temperature of state 2? The saturation temperature at 1 bar. So I clearly know because I have liquid vapor coexistence, that means I am at the saturation point. And that value is also given to us in the problem statement, or I can obtain it from the Antoine equation, minus 0.5 degrees Celsius. Okay, so for the ideal gas model case, or even when you had superheated vapor, so scenario 1, where the superheated vapor in state 1 was more or less a real gas, to be more accurate, you obtained 11 degrees of cooling. Okay, I went from 447 to 436. In this case, we are getting 70 degrees of cooling. So by just changing the state point temperature, I am getting much larger cooling, okay, in my throttle process. So that tells me something which we are going to quantify as one of the problems in chapter 7. The degree of cooling in throttling depends on your state point. Okay, and you can quantify that. Okay, depending on the state point, you can quantify a priori how much cooling you will get. Anyways, so temperature is minus 0.5 degrees Celsius. Any query on that? Why the temperature is minus 0.5 degrees Celsius? And now you can also calculate the amount of liquid and vapor. So if X is the amount of vapor, that is fraction, 1 minus X would be the liquid. X is the only unknown in this equation. You can solve for X. It comes out to be 0.467. Round it off to 3 digits. So that is what you will get for fraction of vapor in the end state. Okay. So now the end state is fully characterized. Now the last aspect of this problem, how to calculate HL sat and HV sat. So I will first need to define a path. for HL sat and HV sat, even though they are path independent properties. However, depending on what kind of information about the two phases, liquid and vapor, is available to me, I will need to define a path in correspondence to available information. So remember, in the ideal scenario, when everything I need to know is available to me, it does not matter what path you take, you will of course get the same value of HL set and HV set. You must get the same value, okay, because they are state functions. However, in practice, in reality, you will get different answers because it will depend on what kind of information is available to you. Okay, so for that, maybe we don't have much time here. Maybe quickly I will show you at least for one path. Okay, so for one scenario I will show you. So I start with the subcooled liquid. At 70 degrees Celsius and 15 bar. Okay. From here, I go to the saturated liquid. At minus 0.5 degrees Celsius and 1 bar. Then at 1 bar, I will add the enthalpy of vaporization so that I can get the saturated vapor at the same conditions, which is minus 0.5 degrees Celsius and 1 bar. Very bad. All right. So this is one scenario. Of course, this is not sacrosanct. You are free to choose whatever path you want. In the next lecture, I will also discuss what are some of the good or bad ways of doing that. Okay. But for now, let's say this is the path I'm going to take. Okay. So enthalpy of my saturated liquid at these conditions. I start from my reference, which is the enthalpy of the liquid at 15 atmosphere and 70 degrees Celsius. Okay. I then first change temperature at fixed pressure. So these relationships are available in the lectures. So I hold pressure constant, and at constant pressure, I change my temperature from 70 degrees Celsius to minus 0.5 degrees Celsius. For this, I need the CP at 15 atmosphere, and I need the CP as a function of temperature. Okay, and luckily that information is available to us. So I know how the specific heat capacity is changing as a function of temperature. That information is available to me for the liquid. Okay, so all of this calculation I'm doing in the liquid state. So this is available to me. Therefore, this is the path I'm choosing. Next, I need to change the pressure now at fixed temperature. One minus beta into T times VdP. And all of this you are doing at minus 0.5 degrees Celsius. You're changing the pressure from 15 atmosphere or 15 bar to 1 atmosphere. Okay. So doing this in systematic fashion allows me to make sure no worry about reference. I start with the liquid at 15 atmosphere, 70 degrees Celsius. I go to a liquid at minus 0.5 degrees Celsius and 15 atmosphere. Then I go to a liquid at 1 atmosphere and minus 0.5 degrees Celsius. Okay. And in this last part, because liquid properties are a weak function of temperature, In principle, even if you completely ignore this last integral, you will not make a significant error. However, the information on beta and the specific volume of the liquid is available to me, in fact, for the entire range. So from 1 to 50, this information is available to me, and even beyond, at temperature of 0 degrees Celsius. So if I'm interested, I can actually do a numerical integration also. However, if you look at the data, I will read out the volume values. So the density values, okay, which is the inverse of specific volume, at a pressure of 1 bar, it is 601.1. At a pressure of 10 bars, it is 602. Okay, so I'm changing the pressure from 1 to 10 bars. I'm making a change of 1 in 600. Okay, so very, very small change, less than 0.2% change. Okay, in going from 10 to 50 bar, I go from 602 to 606 in my density. Okay, so taking VL as a constant from 1 to 15 bar is not a bad approximation. So I take it as constant. Similarly, taking beta as a constant from 1 to 15 bar is not a bad approximation. I take it as constant. So it makes my integration easy. Okay, and that is how I obtained the value of HL sat, which I wrote above. And now if you want to go to HV sat, all you need is access to delta HLV. So how can you get delta HLV? At 1 bar, any correlations are available to you? In this case, I'm going to use the Clausius-Clapeyron equation. Okay, not writing it. So I will use the Clausius-Clapeyron equation. The reason being, the P sat as a function of temperature, that function is available to me, which is required here. Specific volume data for both vapor and liquid state is available to me. So I can very easily use the Clausius-Clapeyron equation to calculate delta H LV, that is the enthalpy of vaporization. So I will add the enthalpy of vaporization to HL sat, and that's how I will be able to get HV sat. So this is one possibility. The next possibility I will discuss in the next class, and that next class will be on Monday. Thursday we have no class. So I will highly recommend, please work on solving these problems yourself before you come to the Monday class. Okay, there is 1 or 2 minutes. If there is any query, you can ask.
Sir, I have a query regarding the our submission we cannot see on the minor of the minor.
I will make it visible. So I want to be able to discuss the exam a little bit so that I am not inundated with emails. So that is why for now I am not making it visible.
Okay, so when you discuss after that, you will be making it available.
Yes. So at the same time, I'll make it available so that while I'm discussing the exam, you can actually see your solutions also.
Oh, okay, sir.
All right, we'll close the class.
Sir, when we are supposed to do that? Next Monday.
Monday.